Welcome back, folks. We're still looking at phasors and how we use them to represent sinusoidal functions. Okay, so I have one already drawn out on the page, and then I'm going to show you some animations to kind of relate the time domain function. So it's a function of time. We'll see what that looks like. And the complex number that we're going to use to represent that function so that we can do circuit analysis with it. All right, so here we go with this. We're still looking at phasors. It's a vector that rotates as time increases. So this is a function with the domain of time. So that's a lowercase t. Maybe not the most artful lowercase t, but that's what it is. Let's make that a little longer. Oh, it's red. Oh, that's horrible. There we go. That's a better looking t slightly. Okay, so I chose just out of thin air. I said, hey, we have a voltage, and it has an amplitude of 8 volts. So the amplitude takes on the unit of the function, and the function can have a unit, and it belongs to the amplitude. That's how long our vector is as it spins. The angular frequency in radians per second is going to tell us how quickly it spins. Okay, so we have another piece of information from that. And then the phase angle tells us where it starts. And we can measure that in degrees or radians. So those 3 pieces of information allow us to represent this function as a phasor. And that phasor is really a snapshot of what's going on at t equals 0. Okay, so we're saying what's happening at the beginning of time, whatever we designate the beginning of time to be. So I can take this function and I can represent it this way. I can say it has an amplitude of 8 and it has a phase angle of 45 degrees. Okay, so 8 at an angle of 45 is how I would read that, and it does get a unit, volts. All right, so if we represent that complex number, how do we recover this? The first thing I notice is that I have 2 pieces of information down here, and I have 3 up here. So I've already lost the angular frequency as I move to this representation. And that's why we are limiting ourselves to working on problems that have a single frequency in them, because the whole problem will have to be worked with that frequency. If we start to mix frequencies, we got to break it up into subproblems and put them back together with superposition. We're not going to do that yet. Okay, 8 at an angle of 45. So let me do this here. Let's get that set up. Things are going to happen. Get ready. And let's plot that on the screen there. So that's 8 at an angle of, that's 8 cosine 2 pi t at an angle of 45 degrees. Oh, that's a mouthful. Okay, so it looks like it's not quite starting at its peak, and I've chosen to plot 2 full periods of it. So it's going to repeat itself 2 times. This is the time domain representation. We can see along the horizontal we're measuring time in seconds. So with an angular frequency of 2 pi radians per second, we're going to make 2 full revolutions in 2 seconds. Okay, it looks like the peak is up here at 8, and the negative peak down here is at -8. Okay, so that should give us some idea of what's going on there. And we're going to make this spin. Okay, or I'm sorry, we're going to represent this differently. We're going to represent this time domain function. We're going to represent it as 8 at an angle of 45. Somehow, hold on, that didn't work. We're going to represent, let's try again. We're going to represent it as, this works so smoothly when I'm in the class. Let's try it now. We're going to represent that as a vector that can be described as 8 at an angle of 45. Hey, there it is. Okay, so good job, right? So this distance here is 8. Okay, if I were to stand it straight up, it would point up to here. If I were to lay it down, it would come down here to 8. And that initial angle is 45 degrees. So this is where it is at t equals 0. Now, take this and spin it. And what we're really interested in is the distance to the tip of the vector from the imaginary axis. So we're interested in this distance here, and we're interested in how that varies as it spins. So let me steal this for 1 second here, and let's do some kind of simplistic math. I keep saying this is the snapshot of what happens at t equals 0. Okay, let's take this and plop it down on our pad, and what I'm interested in is, oh, that's white, that's not going to work. Let's try orange. I'm interested in this distance. That's going to be the instantaneous voltage, is the distance along the real axis. So if this is 45 degrees and this is 8, and this forms a nice right triangle, then we can figure out what this is over here, what this length is, and that's going to be that's going to be the voltage at t equals 0. So let's try to do that. Okay, I grabbed my calculator. I checked the mode it's in. I'm in degree mode here, and we can take this measurement here. Orange kind of works on both light and dark backgrounds, and we can say that it's 8 cosine 45 degrees. Right, that's what would happen if we plugged in, let's go get this up here, 0 from here. Okay, if I'm evaluating that voltage at t equals 0, then anywhere I have a t, I put in a 0 for 0 seconds. Anywhere I have a t, I put in a 0, which is going to make that whole term, the angular frequency disappears, right? 0, and I'm left with 8 cosine 45 degrees. 8 cosine 45 degrees is equal to, let me read it off my calculator here, 5.66, we'll call it. Okay, and since this is 8 volts, then the answer is going to be an 8 volts there, 5.66. All right, so we're interested in that distance, and we can see that distance somewhere else. We can see it right here. This point at t equals 0, that instantaneous voltage, if I just plot it as a function of time, is 5.6, and then I did a little rounding, 6 volts. Okay, I think that shows up in the video. I hope it does. Let me know if it doesn't. It is 5.657 as I read it with my, slightly aging eyes. Okay, so, but we're going to represent it this way. So we want that distance. As it spins, let's see, it's going to spin in this direction. It's going to get closer to the imaginary axis. So it's going to head towards 0. Okay, then it's going to come out here, and it's going to be down here at -8. Okay, and then it's going to spin back up here. It's going to head back towards 0. Then it's going to come up here. It's going to be up here at +8. And then it's going to finish one full revolution, which we call the period. It's going to finish one full revolution back here at 5.66-ish. Okay, and I think we can see that. And I think we can see that here. So it's going to start here at 5.66. It's going to head towards 0. It's going to go down here and hit a peak at -8. Head back towards 0. Back up to -8, and it finishes its revolution, its first revolution here at 5.66. And it does the same thing. It's repeating itself. Okay, so I want to make this spin really badly. We're interested in that distance, and that's what's going to be fun for us to watch. Let's see if I didn't screw this up. All right, let's make it spin. Ready? It's just going to do this. That's 2 full revolutions. And we're looking at that distance to the imaginary axis. I can do it again. And that distance changing is going to be r cosine. All right, so we don't have to think of it as a vector. Actually, in some ways, that extra line, I almost pointed to it on the screen, this line kind of gets in the way. We can think of it as just the point in space rotating around. Okay, so that might just look like that. It's just a point in space rotating around as time increases. So if I'm going to think of it as this point moving as time increases, it might be useful to add an additional axis. So we're going to make this a 3-dimensional plot. I'm going to stick a time axis straight through the origin and out the other side, and then I'm going to allow the point to spin around, and it's going to kind of corkscrew up as it spins like this. Okay, so it corkscrews up all the way up the time axis here. So as time increases, that point's moving here. I still have the real and the imaginary axis. The real magic comes from keeping track of where that point is as it does this corkscrew up the time axis. So let's do that. All right. And I call it the smoke trail. It's like a plane doing skywriting kind of thing. And we can see that we get this kind of helix thing. All right. And we can, what's cool about this is we can rotate it around. And if we look at it this way, we can see that it does make a circle just like it did before. But what I'm really interested in is plotting how the real component of this complex number changes as it spins and time increases. And I can do that by trying to line this up as good as I can. That's pretty good. So I get the real component, and I see how it varies over time. And if you're paying attention, that kind of looks like the cosine that we started with. So let me get that lined up. Oh, I broke it. Broke it. That's horrible. Sorry about that. Let me try to get that lined up for you. That's going to take me pausing, and I promise you it'll look way better. Okay, I got it lined up better for you. Sorry about that. So here's the time axis along here. Here's the real axis. It starts at 5.66, goes down to -8, back up to +8, -8, +8, and ends over here at 5.66. I'm looking at it head on. This was from tracking that plot, right? What I would like to do is compare that to the time domain plot that we started with. And if I do that correctly, let's try to do that correctly, we can see that they fall line on line. Okay, so we can represent this cosine in that way. It's pretty powerful stuff. It's good stuff. Okay, change it up. You can represent any number you want. This is usually where I'd ask you to pick a number for me. But if I want to draw the phasor diagram for another phasor, right, we'll do that on a complex plane. We get the real axis and the imaginary axis. And where do you want to start it? You want to start it down here. Okay, so let's say that's 2 at an angle of, well, that's 180 and that's 270. Let's call this 225 degrees. Okay, and we can easily make this representation do that for us. We'll leave it spinning at 2 pi radians per second. 225. So let me set that up, and with any luck, I'll do it right this time. Okay, so there's 2 at an angle of 225. Well, it starts at a negative number now, right? Well, it's at 225, so I hope this ends up being the right way for you, but it's down here. So it has a negative real component to start out with, and we see that over here. Okay, we could represent that with this phasor, right? This distance is -1.4 and change, whatever it ends up being, a little less than -1.5, and that's what it's going to start at. So if I come back and look at this, it's a little bit less than -1.45. It's going to rotate counterclockwise, so it's going to head towards 0. Then it's going to get up here to a peak of 2, head back towards 0, down here to a negative peak of -2, and then it's going to end its rotations back here at -1.4 and change. What is it? -1.414. That's a special number, whether you recognize it or not. Okay, and we can see that over here as well. It's going to start at -1.4. It's going to head towards 0, peak at 2. Here's its negative peak at -2, and it's going to end its first rotation here at around -1.414. Okay, let's make it spin. Not this one. Let's make the other one spin, that one. Okay, that rotation, come on, that rotation is going to not work. There we go. There's the rotation. I lost my vector for some reason. We can take that and we can let it corkscrew up the time domain. Okay. We can leave that little smoke trail for our plane. And then if we plot the real component versus time, we get our function back roughly there. I'll make it look good right now. Ready? Snap it. And it's line on line with our original time domain plot. Okay, hopefully you're more comfortable with the idea that we can take a time domain cosine and we can represent it with a complex number, and that complex number is really just a vector that spins, and from that we can recover our original function. Okay, I'm going to take a brief aside and talk about why we can't do this with multiple frequencies in the problem, beyond the fact that we've lost the frequency here. Then we'll start building up how we do circuit analysis with this. Okay, so stay tuned and good luck.